That might be what the chat. Okay, yeah.
Okay. Okay. Yeah. So I will talk about a construction of a quantum field theory, a free quantum field theory, which satisfies equation Laplacian minus constant phi equals 0, and lives on some kind of asymptotically flat Riemannian manifold. So we think about this as a Riemannian analog of free Klein-Gordon fields on asymptotically flat spacetimes. So I want to say right away that this is not an example of what one would usually call Euclidean QFT, in the sense that as far as we can tell, it's not a wave-rotated version of anything Lorentzian. It's more like an object that has the properties of a typical Lorentzian QFT, but is built on top of a Riemannian manifold. At the end, I can say a bit more about that if people are interested. I just want to say right away. But so I'll start by just talking about what we mean by QFT then.
You might need to click on the slides to like focus.
Okay, great. Yeah, so I'll start by just reviewing kind of the basic concepts of QFT in the curved space-time, because that's what we're building off of, kind of in the algebraic framework. So we're looking at a free complex scalar. So informally, we have some field phi of x. It's a complex field, so it's not self-adjoint. We also have phi star of x. And we look at smeared fields, which we think of as this field integrated with some kind of test function over all of spacetime. And this field is supposed to satisfy a linear equation of motion, which will be phi equals 0. Is this going to happen every time someone finds? Okay, sorry about that. So yeah. So now I'll talk about how, so the way this is formalized is instead we take this phi of x to be the basic object. So we choose some space of test functions that we're going to use. And we define a unital star algebra. Star algebra just means that you can multiply things and take conjugates of them. And unital means we have an identity in the algebra. And we define this by generators and relations. So we take the generators to be smeared fields labeled by all test functions. So we have those, we have their conjugates, and we have the identity. And the relations we impose is that it's kind of what we need to respect this interpretation. It's that the smeared fields are linear in the test functions. Well, specifically in this convention, the conjugates will be linear, and then these will be anti-linear. Then this is the equation of motion in the distributional sense. So here I'm kind of cheating. So like this would really be exactly this when P is a self-adjoint, essentially, sorry, a formally self-adjoint operator. We say that instead of P phi equals 0, we say that phi equals 0 on the range of P. Finally, we impose the canonical commutation relations, which is we say that the commutator of two smeared fields, well, basically we prescribe the commutator of smeared fields. The usual ones where two phi's and two phi stars are commute, but phi and phi star don't commute. And generally speaking, just like algebraically, this needs to be some permission form on this space of test functions. And to be consistent with the equation of motion, it needs to descend to this quotient basically whenever f or g isn't arranged in 0. Yeah?
Wait, S not yes, satisfies the equation.
Sorry?
So that means that, wait, there's stuff in S not yes that doesn't satisfy the equation. Or is that?
Well, so the thing that lives in S dot mod PS is the Fs, right?
Do those all satisfy the equation?
No, the Fs are like any space of test functions. So you think of it as like bump functions localized somewhere in space.
Isn't it usually like the thing only is supposed to be things that satisfy the equation?
I think you're talking about an equivalent way that this is sometimes defined. So you're talking about we first take a space of classical solutions, and then we quantize that as like you have some symplectic structure and you quantize that. Yeah, this is a different way of doing this, but it's equivalent. Basically, you can there's an isomorphism between them.
But we're using Fs that don't necessarily satisfy.
Yes.
So it's actually.
No, there's I mean,
It's a different thing. These functions show up in a different place.
Yeah,
These are
yeah.
things you smear the fields by. You're thinking of like the states.
Yeah, I can say that. So like if you have like usually what happens is you take like say f this will be like compactly supported smooth functions, and if you act on this with the difference of the advanced and retarded propagators, you get some space of space compact solutions of your Gordon operator like this, and this if you mod this out by c infinity, then this is bijective. This is the isomorph. So I'm working kind of on this thing.
Isn't P of S like this basic solution?
No. P is the range of the operator, right? This P, the space of solution would be the kernel, right? Okay. Yeah, and so what I was saying was for bosons, and if we're looking at the theory of fermions, we'll impose anti-commutators instead, but algebraically this is still needs to be some okay, so that's kind of the algebra of operators, and then how one defines a state in Keynesian curved spacetime is a prescription of expectation values for every algebra element. So this is a linear function on the algebra, which is normalized in the sense that the expectation identity is 1. And we have this positivity condition that all elements of this form have positive expectation value. And this is because the thing we're generalizing is kind of this type of their product, right? Which would be just the norm of the state, A. So yeah, this is what we call an algebraic state. So this is like a pretty general condition, and like in any given model, this might include states that are very different from states. Okay. Then I will only consider states which are called, first of all, quasi-free states. So this is the same. This is another name for Gaussian states, basically. So in general, a state is completely determined by its values on all monomials of phi's and phi stars. But for quasi-free states, you only need to know its value on the 2-point function, so phi and phi star, like this. And everything else is determined in terms of them by some kind of wig formulas. Yeah, and technically, because we're looking at complex fields to get this property, we also need to impose something that's called gauge invariance. So in this case, gauge invariance isn't very deep. It's just that complex fields represent charged particles, and we have a global invariance under we're scaling by a phase of all the fields, and this is just if we also restrict states that are invariant under that. Basically, we're left with basically every state is determined by these two pieces of the commutator. Right, so we had the commutator was the difference of these two things. And I mean, in fact, one of them determines everything because they're different.
Do these type of states exist in interacting quantum field theories? Is the constraint on field theory or just a class of states you find them in?
So for an interacting field theory, you would already have to change this framework because it's kind of using the linear structure. But people do construct interacting field theories in algebraic perturbatively. Yeah, I think there might be additional conditions that you need besides this, like there you won't have just bits. Okay. And yeah, and you can just algebraically show that these need to be positive permission forms. It's not like immediately obvious, but it's true. In fact, for any positive of positive permission forms, which descend to the quotient and which satisfy the commutation relation, you have a unique state.
Just make sure that also you're saying the quantity states of the state that are the, so any state that is determined, but the function is important.
So there is a specific definition of them, which I'm not giving here, which is basically tells you, like expresses all of the endpoint functions in terms of these things, and that's the definition of what's yeah.
But I would have thought that in the pre-field theory, every state was like that. Is that not true?
Not really, because at least like with this definition, you can prescribe independently almost any endpoint functions. Well, you have like the constraints of the commutation relation, but not every state has to be Gaussian.
Also, there are excitations of the vacuum that aren't Gaussian, right? In Minkowski.
Yeah, but I would have thought that you could always have reduced it to point function with contraction.
Excitation of the vacuum can go on.
And I think you might also end up with some of the like phi phi's and phi stars, imperial and phi phi. Yep. That's a good question. I don't think so necessarily because like this is not a linear function, but I don't know, maybe
It's like the linear vacuum example.
Okay, I don't know, but I think wait, the Rindler vacuum
Divergent. But it should be like
is it? I think like most of these kind of basically any vacuum state is usually a Gaussian state. Yeah, I haven't looked at specifically like this. Okay. Yeah, but kind of at this point, yeah, I'm not going to go too much into kind of like going deeper in this direction. I'm just going to say that constructing these kinds of states is equivalent to constructing pairs of positive permission forms that satisfy the commutation. Kind of you instead of constructing states, you can construct two-point functions. Okay. So now I'll go over the basic example of kind of the most commonly described quantum filters. This is the Clagborn field on a globally hyperbolic spacetime. Globally hyperbolic spacetimes have unique advanced and retarded propagators for Clagborn equation, which we think of as solution operators, inverses for this operator. And so we'll take the space of test functions to be the compactly supported smooth functions. The commutation relation in this case is given by the difference of the difference of these propagators with an I. And this does give you 0 on the range P because these are two inverses of P. So if you apply this to P times any test function, you'll get 0. And the reason why this is, well, you can just do the calculation and like take these kind of formally to be delta functions and see that this gives you the correct like delta equal time commutation relations. But kind of physically, the relevant thing here is that the difference of these things is has 0 support for points which are space-like, has no support for points which are space-like separated. So this gives you kind of fields commuting at space-like separation. Yeah.
So is one way of thinking about P of S is that like sort of field that
P of S.
like
Action the equation motion of.
Yeah.
P is the operator.
is P of S like the set of all like test functions that we experience and
It's the set of all test functions that when you integrate them by parts, you end up with the equation of motion acting on the field. So those things are all supposed to vanish, because the field itself is supposed to be a solution of the equation of motion.
Yeah, it's not. Yeah, it's just not part of the space. Yep. Thanks. Okay. But this is kind of the usual construction, and often when we think of the 2-point functions, we actually represent them by linear operators. So we can instead of looking at this Hermitian form, we can look at like function f but integrated against lambda g. This and given any particular state which we encode in these 2-point functions, one can define Feynman propagators by this combination of retarded or advanced propagators and the 2-point functions. So just by the commutation relation, this is equal to this and this. So I mean, this might look like kind of a random expression, but the important, like the reason why this is the definition is because, first of all, these are also inverses for the wave operator, for the Klein-Gordon operator, because right, the G's are inverses and the lambdas are actually solutions of the Klein-Gordon operator. And the reason why we take these specific combinations, because that makes their kernels be the time-ordered Grace functions, which is what one calls Feynman propagators usually. So these are kind of the operators you get from Grace functions. And so this one is technically the Feynman one. This is the anti-Feynman one. This is, of course, this is what goes into scattering amplitudes, and even in curved space-time, this is an ingredient of perturbative interactivity. Okay, but like I want to emphasize that in this framework, these Feynman propagators are dependent on a state, right? And usually when we talk about TFT on flat space-time, you talk about Feynman propagator. But that would be like the Feynman propagator of the vacuum state, the Minkowski vacuum. On curved space-time in general, you don't have one preferred vacuum. So you have a Feynman propagator for every state. Which would be the time-ordered Green's function in that state.
and in curved space like how do you do the ordering?
So if we're looking at a globally hyperbolic space-time, there is you can choose a time function, and basically you can see that here the choice of time function. Yeah. But you're right that it's kind of awkward because a lot of things do depend on the choice of time function, and kind of you can just take these as the definitions, and here you don't have to look at the kernels or the time ordering. You can just combine these algebraic objects. Okay. So yeah, so that is kind of, those are the main ingredients of QFT and Hertz space and that we'll be concerned with. And now I will switch gears to basically what I want to come to is to just talk about propagators from the perspective of microlocal analysis, because that's the mathematical technology that we use in our construction. And in general, it kind of illuminates what a propagator is. So I'll start by just talking a bit about the basic concepts of microlocal analysis. And yeah, so please let me know if you want to discuss something in more detail, because I mean, I do want to get to the Euclidean construction in the end, but it's also fine if we spend a lot of time talking about the general framework, which is in the Lorentzian. It's just that the Euclidean part is the one that I contributed to myself, but it's interesting. Yeah, so the main concept of microlocal analysis is the wavefront set of distribution. So we're looking at distributions on a spacetime. So to build up to the wavefront set, we can look at first what does it mean for a point to be in the support of a distribution, right? Unlike smooth functions, distributions aren't really defined pointwise. So the way you define that a point is in the support of a distribution is if you can multiply it by a smooth, compactly supported function, which is not zero at this point, and you get the zero distribution out of this, right? The zero distribution. So this is saying that kind of you might have stuff happening far away from X, but if you localize to a neighborhood of X, you're zero. Kind of a more refined version is this concept is the singular support, which is the same thing, but you say that this phi u is a smooth function after cutting off. So if you take basically if you have a delta function, then it's anywhere except at the origin you can multiply it by a small bump function and get zero out of it. But any function which you multiply with, which is supported at the origin, is going to give you something with a singularity at the origin. So both the support and the singular support of the delta function are at the origin. Okay. And now the wavefront set is a refinement of this, which lives now in the cotangent bundle, or in flat space, you can think of it as you have a point and a vector at this point, a direction at this point. So we say that a point and a non-zero covector at that point are not in the wavefront set. And yeah, here I should have said the same, right? This would be like X being not in the support and X being not in the singular support. So here xi is not in the wavefront set of U. If we can localize near X, then we take the Fourier transform, and there is some direction in which this Fourier transform decays rapidly. So rapidly here means as a Schwartz function, so faster than any polynomial. And so this is saying, right, because the Fourier transform in any given direction is related to derivatives, directional derivatives in that direction. This is telling you that your distribution is, so if in some direction it does not decay rapidly, it means that your distribution is singular at that point and in that particular direction. And this can be generalized to manifolds using local coordinates. And I will just give an example just to illustrate the main idea. If you have the distribution in two variables, here just in flat space, which is the delta of x, just one of the variables, then so this is smooth everywhere except the vertical line x equals 0. So we have the plane. It's smooth except here. And it's singular specifically in the directions crossing across this, because if you're here but you're moving along x equals 0, then it looks constant. So this is the idea behind the wavefront set. So the wavefront set distribution, if you can calculate it using Fourier transforms pretty easily also, and you get what's called the conormal bundle of this thing, which in this case is the points where x equals 0, and the covector has only non-zero components in the x direction.
Yeah. Or you know what wavefront like. Also be like
Yeah. Well, if it's a smooth wave, there would be no wavefront set because you only have a wavefront set if something has a singularity. But if you have like a sharp wavefront, then it would be wherever the wavefront is and going in the direction of where the wavefront is. Okay. Yeah, but kind of the general idea is that you can. For a distribution, you can track not only where it's singular, but also in what direction it's singular. Okay. And so now, when we look at operators, say an operator that's mapping test functions to distributions, it can be represented with an integral kernel, kind of formally like this. Any operator, any linear operator from the function distributions can be represented by this type of integral. And the connection to the connection to wavefront sets is that if you can describe basically what happens to the wavefront set of a function under action by an operator if you know where the wavefront set of the kernel is, right? Because the kernel is a distribution on the product space with itself. And we define this prime wavefront set, which is basically just the wavefront set of the kernel, except there is a minus sign here because of how everything works out in these expressions. So, I mean, this looks kind of complicated, but the relevant thing is that if you act on a distribution by an operator, ignore the second line for now. The place where you can have wavefront set at the end is the points. First of all, it has to be kind of in the projection of the prime wavefront set of Q. And it has to be kind of related to where the wavefront set of the original function is. So it's the points in the wavefront set of the wavefront of the operator, which are also points in the wavefront set of the original. Yeah.
It's a little hard for me to parse so many equations at once. I'm wondering if you could, I assume you're talking about all this because you're going to want to apply this technology to the Feynman propagator of something in a curved spacetime.
Yeah, it's coming very soon.
Okay, is there any way you could signpost for us, you're telling us something about wavefront mapping properties. This is going to be like if you use the Feynman propagator and you act on something that has certain wavefront properties, you get some different wavefront properties out.
Yes.
Can you signpost for us what this is going to be telling us about physics, or sort of how this is going to be something that we should be caring about at this point?
Yes. So the idea is that propagators. So we have this general idea that say a retarded propagator propagates things into the future, and advanced propagator propagates into the past. And Feynman propagators, the way we think about them, is that they propagate positive frequencies into the future, or positive energies into the future, and negative energies into the past. And the way one can actually formalize them is by looking what happens to the wavefront set of a function when you act with these propagators on them. And yeah, I think it's probably the very next slide. So yes. So yes, the wavefront set is the set of points. It's kind of it's a combination. It's a set of points where a distribution is singular with the additional information of in which direction it's singular.
It depends on the state.
So right now there is no states. Right now there's just distribution.
the
Yeah.
distributions that you're going to want to apply this to come from quantum field theory in some way.
Yes, there will be like field configurations, I guess.
What's the code? That's the direction.
Yeah, so I think like we don't really need to worry about the distinction between covectors and vectors at this point. But yeah, you can just think of it as the direction in which it's so here so there is no test line here. Okay, right now here this is pure math. We have a U, which is a distribution. This is the space of distributions. And
That's not a test. That's the maps.
yes, because okay.
Can you maybe say what is the object in quantum field theory that you're going to want to apply this to?
Yes. Let me go forward.
Or U is just, it's sort of like halfway, you're using more distribution instead of test line. But like, because I'm not a mathematician.
Yeah.
Okay.
Well, I'm not using it instead of test function because distribution is kind of the opposite of a test function, right? Because distributions is something you can act with on test functions. So test functions are kind of infinitely nice. Test functions have no wavefront set ever. Distributions have test functions, and what I'm going to want to do is basically, okay, the way to think about this is, let me go back. Yeah, maybe you can spend more time on this. So we think of these smeared fields as the basic object, right? But when kind of to connect this to physical intuition, you really think about something that's peaked very sharply at some point. So you might think, like for example, if you want to actually think about the object phi of x, the quantum field phi of x, you would think of f being a delta function. So to kind of a priori, you define this whole structure for test functions. Yeah? So something infinitely nice. But then once you have it, you can try to extend this to like various classes of distribution. And you won't be able to extend to arbitrary distributions, but there will be kind of some singularities which are allowed. And where is this? Yeah, so here, so you'll singularities will be allowed, and you're going to be looking at 2-point functions like this, and you're going to basically, if you want to think of f and g here as representing some, I don't know, some number of particles somewhere, then there will be something singular, and you will want to think about how this acts on basically. For example, like the very specific question is like, what classes of distributions can you extend a state to? So kind of how singular can you or something to be? That will depend kind of on when this object is well defined, right? Everything is well defined for test functions because they're very nice, but you can't just integrate two distributions against each other. That's like the great tragedy of interacting quantum field here, right? You can't multiply distributions together. If you can make sense of this object for certain kinds of distributions, that means you'll be able to extend your notion of a state, and that will precisely depend on kind of what these lambdas do to the wavefront strategy. Because if two distributions have wavefront sets that have nothing to do with each other, you can multiply them because wherever they are overlapping, they're basically smooth functions.
I'm sorry, I don't know. But it's a quick question. So lambdas here, what is the capital lambdas? Where are the capital lambdas?
It's just we represent 2-point functions with an integral kernel. So it's I'm saying that like any permission form, right? So this is supposed to mean omega of phi of f phi of g, like this, right? For the state omega. I'm just saying that you can represent it as some integral of x and g.
And then there's operators.
Yes, yeah. Okay. Okay, yeah, maybe let me move to kind of something a bit more conceptual. So, okay, so yeah, the question here was how to characterize propagators. And so there is kind of a precise version of this idea that retarded propagator propagates things to the future, advanced propagator things to the past, Feynman propagator propagates positive frequencies to the future, negative frequencies to the past. This comes up when you study. So we were saying that the propagators are inverses of the wave equation of the wave operator, but we can consider inverses modulo smooth functions. So basically, operators which will take basically we act with Q on P of F, and this is going to give us F plus some smooth function, right? And this is a non-trivial statement if we want to consider them acting on distributions, right? And the idea then is that you can define distinguished classes of operators like this, which are called parametrices, by saying that they propagate the wavefront set only in a particular direction. So just by kind of general mathematical theory, you can show that these these propagators only have singularities on the light cone, then you can say, let's call a Feynman parametrics any parametrics which propagates wavefront set in like in the positive light cone, it propagates wavefront set to the future, and the negative light cone it propagates wavefront set to the past. So basically, if you are acting with, let's say, our Feynman propagator will be like this QF. It acts on some function f, and we're going to say the wavefronts, if like, let's say this is the light cone, then and let's say here we had some wavefront set of f. Then the wavefront set of this thing would be somewhere kind of in this region, and union with this region. Okay, maybe I should say, because I haven't said this explicitly, right? Is that when you do this in normal quantum field theory, the way you do this is you Fourier transform everything in sight, and you look at where kind of what happens to the Fourier modes. The reason why you even want to look at this microlocal technology in the first place is because in the curved spacetime, the global Fourier transform is not usable because you don't have time translation invariance. Like this is the thing where even though you can define a time function on globally hyperbolic spacetime, things like your metric will be time dependent. So if you you can't really split things into time frequencies which interact nicely with the wave equation, right? Your wave equation will no longer turn into a polynomial. So this is kind of a generalization of what you would say with Riemannian. Yeah. But okay, let me just kind of I mean, I'm definitely not going to be able to go through everything, but I want to say some things which are kind of ideas which are interesting here. So you can give these kind of microlocal conditions for like microlocal definitions for what a parametrics of each of these types is. And the retarded and advanced propagators, which are well defined, like on any global spacetime, they're always parametrices of this type. But the Feynman and anti-Feynman propagators, remember, they were defined, they were state dependent. And it's a result of Minkowski that they're going to have kind of the correct singularity structure only if they're defined for a state which satisfies the Hadamard condition, which is a condition which is it's basically a version of the condition that you have finite energy density everywhere, physically speaking. But this is a condition which is often used to kind of single out physical states of QFT in curved spacetime.
So in your language, the Hadamard condition would be like what condition of the two-point function?
Yes, there will be it's a condition on the wavefront set of the two-point function, because the two-point function is so though if we look at the two-point function as an operator, right, like this big lambda, then it can be represented by a kernel, and the kernel has a wavefront. That's kind of how it formally, right? And yeah. And this was drawn in the paper by Minkowski, basically. So it was quite a bit after physicists started talking about that. Okay. This is kind of the one of the main ideas here is that these parametrices are only unique modulo C infinity terms because they're originally defined to be inverses only modulo C infinity terms. So for the advanced retarded ones, you have kind of canonical choices of propagators from the class of parametrices, because you can just say, right, the way you usually define the retarded propagator is it's the inverse of the wave operator, such that basically which is 0 in the forecast, or which only propagates support in the future. So there is kind of a unique choice there, but what about the Feynman versions? So they're kind of there are different possibilities. One thing which is kind of very physically relevant is you can just choose a preferred Hadamard state and work with and define your Feynman propagators relative to that Hadamard state. So this is what you do in Minkowski when you're say the Feynman propagator is the Feynman propagator of the vacuum state. And more generally, you can, in spacetimes, what symmetries you might have a state which is invariant under the symmetry. So you were talking about the Rindler vacuum. You can have in black hole spacetimes, you might be interested in considering a particular state. So in any given problem, you might just be concerned with a particular state. But it's also an interesting question whether you have kind of for whole classes of spacetimes, you can define a Feynman propagator which only depends on the spacetime and not on like some chosen state. And one approach to doing this is kind of, which mathematically looks nice, is that you can choose natural function spaces and look for a parametric that is going to be an actual inverse, right? Because we were talking that these propagators are supposed to be inverses of the wave operator, but like they're not actually inverses. Like the parametrics are not actually inverses. But if you can choose kind of function spaces in which things live naturally and demand that the propagator be an actual inverse, this might single out a particular parametrics. Okay, I think I want to probably skip forward to basically a situation where we have this, so I can talk about more physical things. There is kind of quite a bit of technology that goes into this, but in the end of the day, you get kind of so for example, in the Lorentzian setting, there is this class defined in yeah, I think this was defined in this paper by Vasy and Wrochna, called non-trapping Lorentzian scattering spaces, which is basically a class of spacetimes which at infinity look like Minkowski space, and in the interior don't have any trapping, any trapped geodesics. For them, you can define, at least like when it's close enough to Minkowski, you can say that the wave operator is invertible between certain function spaces called the weighted Sobolev spaces. So it's like it has two orders, which basically say like how smooth your function is and how fast it's basically. Anyway, you have inverses, and then you basically mimic this construction for Klein-Gordon global hyperbolic spacetimes, where you take the difference of two inverses of the advanced and retarded propagator, and it's going to give you a version of this map. It maps kind of some space of test functions into some space of solutions, and it's going to be a permission form on the space of test functions, so you can use it as basically to define your commutation relations and to talk about quantum fields. And okay, I kind of skipped over the details, but these function spaces, they it's not just some random space that has nothing to do with, originally, right, these had a very nice interpretation in terms of going forward in time, backward in time. So here also they will have you have function spaces which have the functions there are more regular in the future relative to the past, or vice versa. Okay, so I will talk a little bit about the Riemannian inversion, which is actually easier. I hope maybe we can be more illustrative. So kind of the geometric setting here is what was called by Melrose Riemannian scattering spaces, which is you have a manifold with boundary, and you have a metric that at the boundary goes like this. And here x is a boundary defining function, which means that if you think of a ball, it's a function of 0 at the boundary, but vanishes simply there. So it vanishes to first order. And then kind of this tells you how the metric behaves at the boundary. And this is actually not some completely random class of spaces. Actually, if you just take Rn and you compactify it into a ball, by taking any line through the origin and adding a point here, so it gets compactified radially like this. Then the Euclidean metric is actually of this form. If you take x to be some smooth function that goes as 1 over r, and you can just do chain rule and see this is exactly the right powers x. So an example of this is just Rn. And you can on Rn, a nice class of functions is the Schwartz space, which is functions that functions that fall off faster than any polynomial. This gets generalized to functions which vanish to infinite order at the boundary. And you can also look at the distributions associated with positive test functions, which generalize the temper distributions. Now what we look at instead of the Klein-Gordon operator is the Laplacian minus a constant. It looks like this, plus some lower terms in the precise sense. So you can see that it's built out of x squared dx and operators on the boundary, like in the transverse variables multiplied by x. So this is called the scattering differential operators. This class of differential operators. The point is that so it kind of looks formally like the Klein-Gordon operator. But especially so if you take specifically a space with two boundary components. So I guess I really want to if I want to make this clear, I really have to go through some of the elements that go into this. So yeah.
What was H for the just flat space example?
Wait. This?
Yeah.
No, this is the metric on the sphere, right? This is just
radial coordinate space.
Yeah. So this is yeah. So here, this just looks like the ball, right? And this is just going to be R, and this is going to be some like the metric. Let me think about what the way to do this. Yeah, maybe let's just forget the Riemannian version. Let me talk in more detail about the idea of how one basically how one goes from the math to the QFT. Is okay with? Yeah. Okay. So the idea is that you want to, yeah, what do we want? We wanted to build propagators as inverses of the Klein-Gordon operator on some spacetime. So what are the kinds of spaces that we look at? So we look at we compactify the spacetime. So also let's just think about Minkowski space. Just we compactify it to a ball in the same sense. So this is different. So different from the usual Penrose diagram compactification, because in the Penrose diagram compactification, null infinity is big and time-like infinity is small. But here, like null infinity is just these points, and this is time-like infinity, and this is space-like infinity. We look at spaces of functions which are so these are weighted Sobolev spaces relative to L2. So the general idea is that we have this space HS, which is basically distributions U, such that if you act with any S, if you act with S derivatives in U, it's going to be an L2. So kind of the more the higher S is, the more smooth your functions are. And the weighted sublift spaces are just they in addition have decay towards the boundary, where here x is a function which is x equals 0, so you should think of x as 1 over r, where here r here, since we're using this kind of weird compactification, would be actually like radial in both r and t. So it's just measuring decay kind of uniformly towards all infinities. And the kinds of the Klein-Gordon operator is a second order operator, second order differential operator. So when you you lose two derivatives when you act with it on anything. So in general, it will map like h as r to h as minus 2r, where like nothing happens to the decay order because it's not like the coefficients don't decay at to infinity. And for but this is going to be non-invertible, very non-invertible in general. So this is almost invertible for operators which are elliptic, but the kind of wave operators are not elliptic. So we look at we kind of accept that we lose one order, and instead we look at these spaces here. So we're saying, let's look at the operator mapping from the sublift space to something which only goes one order down, and also gains one order of decay. And between these types of spaces, it's possible to show an invertibility by basically piecing together, but by this kind of strategy. So you want to show, like invertibility would mean that PU in this space implies U in this space. But we will be able to show that assuming that U is a priori in a good enough space. And basically the way, I'll just quickly say that the way you do this is by thinking microlocally, because notice that we are, so we were talking, I was talking about the wavefront set, which tracks where a function is smooth and in which directions it's smooth. Similarly, you can think about where a function is in any of these spaces. So this is kind of finer regularity, right? Something is smooth. If something is smooth, it's going to be differentiable to any order. But you can look kind of locally where it fails to be differentiable a certain number of times and in which direction. So you can think of this in phase space, and then you can piece together information about like you start off an argument that somewhere you have U in this class, and then you are able to propagate that information to everywhere else on the space-time using propagation of singularities theorems, which basically connect wavefronts, the wavefront set at one point, the wavefront set at other points within in phase space.
So bigger picture question about this. So
yeah, let me just maybe I think because we did just hit an hour, and I think I'll just stop here with the details. Yeah, but please do.
Let me ask the question. The thing I'm trying to understand is that, so you have the wave equation, and you're looking for inverses to the wave equation that you can interpret as Feynman propagators.
Yes.
And this is supposed to characterize for us, the different ways that fields, dynamical sort of quantum stuff can propagate in curved space-time
Yes.
theory of free quantum fields. Now, it seems to me like if we're looking at sort of compact, smooth sources, then this isn't a very difficult problem. Like the inverse, sort of the structure of the inverse is just sort of the natural thing constructed from the advanced propagator and some solution or something like that. But what I'm understanding from what you're saying here is that if you want to look at how you propagate asymptotic data, then something more complicated happens. Is that a way of thinking about what's going on here when you compactify and you start looking at the regularity of these things that behave in a certain way?
Yes. So the behavior at infinity is very important here in the sense that so I don't think you can say that it makes things harder because so when you're talking about things which just like when you're ignoring the behavior at infinity, right? You have this freedom of choosing a Feynman propagator, even for very smooth things, because you still have this modulo smoothing, like these.
But if I made a bad choice, then I might not be able to extend this propagator to things that I might want to consider because they would represent, for example, scattering experiments in space.
Yes. So if like basically if what you want to consider is like a particular experiment, and you might want to model that as like some number of particles in, some number of particles going out, things like that, then kind of, yeah, you like modulo smooth is not good enough for you because you want to be able to like when you, as you're saying, when you extend to infinity, you want it to represent your kind of initial conditions. Yes. Yeah. So yeah, I just want to say that kind of the kind of one interesting idea that I think comes out of this whole framework is that there are like different ways to think about what a Feynman propagator is, and it's not necessarily obvious what is kind of the correct way to think about it. So you have these propagators that are connected to particular states, or you can have propagators that are based on particular structure at infinity. And in the flat space-time, they're kind of like a lot of things coincide by accident, kind of, but in curved space-time, kind of there are a lot of interesting questions to be asked. Yeah, but thank you, and yeah, I'm sorry this got off track a bit, but I hope everyone got something interesting out of it, and yeah, I'll be happy to answer any questions. Yep.
Right, we have time for a couple quick questions if anybody has any.
So you described this setup where in Lorentzian sort of global hyperbolic spacetimes, there might be many things you could think of as Feynman propagators, and there are constraints on which ones you choose to be the right ones that have to do with like what sort of asymptotic scenarios you're considering in terms of scattering experiments. So I can obviously see how that might be something that we might want to think very deeply about for studying QFT. Now, I know you didn't have time to talk about the sort of the work that you did, which it sounded like you were doing something, a similar construction in Riemannian manifolds, where you were able to, because you had some asymptotic structure, you could set up a similar question. I guess maybe, would you be able to just big picture say, even if you can't tell us about the details of that work, what you think you learned from doing it and what it might be able to teach us going forward about how to do QFT and Lorentzian signature? If that's even something that you think you learned from.
No, I think yeah, there are some interesting things. Like I don't think there's a single. So one thing that is very different in Euclidean signature is that what you think of as the Feynman propagators in that context is actually no less natural than the like causal and like the retarded and advanced ones, because so this is also in like normal Euclidean QFT, you get this thing, right, that after Wick rotation, kind of the usual kind of limiting absorption principle inverse of the Laplacian is related to the Feynman propagator, right? And not the other propagators. So so the thing that I would describe as the analog to the Feynman propagator would just be what we usually think as the inverse of the Laplacian, and the kind of retarded and advanced ones wouldn't even appear unless you consider this situation where you have two ends to the Riemannian space. And this is kind of bringing into focus the fact that kind of from the perspective, at least from the mathematical perspective, like this perspective of microlocal analysis, Feynman propagators are like, you don't have to think of them as something that's derived from the advanced and retarded propagators. And for the wave equation, the advanced and retarded propagators are kind of natural when we really care about locality, because they come from thinking about the Cauchy problem and the finite speed of propagation of solutions. But if we are in a situation where we care about behavior at infinity, we have to kind of think about global properties anyway. And in that case, the Feynman propagators are also very natural objects to study. So yeah, I guess like directly answering your question, just like the fact that the Feynman propagators are worth studying as their own object as opposed to something built out of advanced and retarded propagators is one interesting thought.
All right, well, let's thank Mikhail again for a great talk.
Yeah.